Okay. So in the last class, we kind of arrived at the Schwarzschild metric by using some uh, simple argument using special relativity and Newtonian gravity. And then we said that that although it seems like it's a solution simply because uh, all the assumptions that we have made are consistent with flat space solution to uh, Rmu equals 0 equation. So therefore, uh, one would think that the solution that we have obtained by just using special relativistic argument should be a solution to the Einstein equation uh, in the in the space where there is no source. Okay, but let's not do that again. Let's kind of try to derive that equation by actually solving the Einstein equation. And we last time we stopped at this point where I said that if you choose the metric to be minus a of rho times dt squared plus b of rho times d rho squared plus rho squared times d omega squared, where d omega squared is a metric on the two-dimensional sphere, then you can show that the off-diagonal components of the Riemann tensor vanish, Ricci tensor vanish, and non-vanishing components are all diagonal components, and r rho rho, r t t, r theta theta, and r phi phi are given by these quantities. Okay. Uh, Now, of course, to do this, you need to do some other computation, which will be part of the exercise. So, in some sense, the exercises are listed in a little wrong order, but nevertheless, uh, if you do, if you get this, then you would have done the other exercise already. Okay. Now, if you really look at these expressions, you will see that only three of them are independent because r phi phi is just r theta theta times sin squared theta, and since each component has to vanish, if r theta theta vanishes, r phi phi vanishes anyway. Okay, so therefore there is no new information that r phi phi really carries. Okay, and that is not very surprising simply because that is kind of dictated purely by spherical symmetry of the problem. Okay, so we have basically three equations to deal with. They are clearly nonlinear and coupled because equations contain A as well as B in them, and in a reasonably nonlinear way. Okay, but nevertheless, they are not that difficult if you really stare at them, because if you look at R rho rho and RTT part of it, the first term A double prime by A versus A double prime by B comes with a factor like half versus minus half, and similarly there is a prime by A versus A prime by B multiplied by the same function sitting around, and then there is a term which is B prime by B versus A prime by B, which also look very similar. So if you kind of stare at it, you realize that if you multiply R rho rho by A of rho and RTT by B of rho, then the denominator pieces, which were the ones which had a mismatch, will all go away. Okay, so B of rho will go away from here, A of rho will go away from here, and the terms start looking very similar. So now we can try adding and subtracting them to kind of get simplified expressions. Okay, so that is what we will do. Okay, so of course each component has to individually vanish. So therefore, one could try to solve them as it is, but of course that is more complicated. But as I said, that if you multiply by A of rho to R rho rho and B rho times RTT and add, then you can check here that there are relative signs here. So if you add, this term goes away. If you add, this term also would go away. And what survives is only this. Okay, because they are the ones who have same sign. So you get terms which is like 1 by rho times B prime and A prime factors, and that is what you get. Okay, so what you will get here is something like this. Okay, now if you stare at it, a little carefully, then you will see that it is written in a little complicated way. But the thing is that in the R rho rho, when you multiply by A of rho, then the denominator pieces go away here, but not there, because there is a B sitting around in the denominator. So the better way to do this is to pull B of rho out of this entire expression, and that is why writing it in this fashion makes it look nicer. Okay. Now that, of course, we have to set this quantity on the left hand side to be equal to 0, because R rho rho and RTT are individually 0. Okay. But right hand side can be 0 only if the term in the square bracket is 0, simply because uh, this has to be true point-wise for every value of rho. And clearly, 1 over rho and 1 over b of rho are not 0 for every value of rho, and therefore the square bracket should vanish. Okay. But the square bracket itself, if you look at it, is a total derivative. If you take d by d rho of a rho b rho, then it will give you the term inside the square bracket. Okay. So therefore, a square bracket being 0 implies that d by d rho of a rho b rho is equal to 0. Okay. But that just tells you that a rho times b rho must be constant. Okay. Now, this constant is not very important for the following reason, that a rho is a coefficient of dt squared term. Okay. And our metric is independent of time. Remember, it's a static metric that we are looking at. Okay. So no metric component depends explicitly on time. So therefore, we can always rescale time and nothing happens to the metric. Okay. Except for getting some factors in front of dt squared piece. Okay. So by doing that, you can change the factor sitting in front of a rho, and so suppose you take t going to a times t, then the factor sitting in front of a rho would go from a rho to 1 over a squared times a rho. Okay. So by doing that, you could kind of convert a rho b rho to 1 over a squared times a rho b rho. Okay. And therefore, if this quantity was a constant, you can just adjust this small a appropriately to set this constant to be equal to 1. Okay. Now, advantage of setting that equal to 1 is that if you set that equal to 1, then it tells you that a is inverse of b. Okay. So that is a good thing for us, because in subsequent computation, we can, every time we encounter b of rho, we can write that as 1 over a of rho. Okay. And try to convert everything in terms of a of rho or everything in terms of b of rho. It doesn't matter which one you want to choose. Okay. So I think we are going to keep b of rho and get rid of a of rho. Okay. So here's the equation now. So let's kind of step back and look at r theta theta again. Okay. Now r theta theta has a term which is -1 plus rho upon 2b of rho, but there's a prime by a term sitting around here. Okay. So what we are going to do is to look at this term and replace this term by writing it in terms of b. Okay. Now that is something we know, because a of rho times b of rho is equal to 1. Okay. So therefore, a prime of rho is minus b prime of rho by b squared. Okay. And that is a fact we can use to convert plus a prime by a into minus b prime by b. Okay. Are you with me on this?
Yeah, it's okay.
Okay. Okay. So, and because it has switched the sign, these two terms just add up, and you get a kind of single term and get rid of this factor of 2. Okay. Now you just multiply this entire stuff by b squared. R theta theta is equal to 0. So therefore, if you multiply the whole thing by b squared, you get terms which do not involve any denominator. And you get minus b squared plus rho times b prime plus b is equal to 0, which is what this equation is. Okay. And remember, b is only a function of rho. So therefore, what we could do is kind of rearrange this equation. We write this as rho b prime is equal to b into 1 minus b. Just take this first term and third term on the right hand side. Okay. And then you can take b into 1 minus b downstairs and convert this into db by b into 1 minus b is equal to d rho by rho. Both sides can be actually solved. this will give you log rho term, and this one, of course, requires partial fractions. Okay, so that is kind of trivial. You can just show that this quantity in the denominator can be written as 1 over b plus 1 over 1 minus b. Okay, if you do that, then this integral is trivial. db by b will give you log b, and db by 1 minus b will give you log of 1 minus b. Okay, with a minus sign, of course. Okay, so that is the answer. Okay, so this, of course, is a constant of integration thing, but log a plus log b is log of a times b, so that's how you get this expression. Here you write this as b upon 1 minus b, so that is this. Okay, and you get b upon 1 minus b is equal to c naught times rho. Okay, so of course this expression can be inverted, and once you invert, you get an expression which is c naught rho upon 1 plus c naught rho. Okay, which can further be simplified to write it in this particular form: 1 over 1 plus 1 over c naught rho. Okay. Fine. Now we can use the fact that a rho times b rho is equal to 1, and therefore that tells you that the quantity in the denominator must be a rho. Okay, so we get a of rho to be 1 plus 1 over c naught rho. Okay, good. So this tells us that our metric would take a form which is like this: d tau squared is equal to minus 1 plus 1 over c naught rho times dt squared plus 1 over 1 plus 1 over c naught rho times d rho squared plus rho squared times d omega squared, which is the line element on the two-dimensional sphere. Okay. So now remember, what we have done so far is to use a relation of this type: a times r rho rho plus b times rtt equals 0. That's what we use. Okay. Now, in reality, what we want is r rho rho equals 0 and rtt equals 0. Okay. The second equation that we have used is r theta theta equals 0, and that is, of course, fine. That there is no problem with that. Okay. But the fact that this equation is equal to 0 does not necessarily mean that either r rho rho or rtt is equal to 0. So what you could do is to check that with this form of the metric, okay, without even worrying about what C naught is, okay, this form of the metric actually sets r rho rho equals 0. If it does, then it is clear that RTT is also 0, simply because in the first equation, a times r rho rho plus b times RTT equals 0. If r rho rho is equal to 0, then for arbitrary rho, RTT better be 0. Okay. So this is a useful exercise to kind of convince yourself that this is actually a solution. And it's not that like only a one particular linear combination of RTT and R rho rho is being satisfied. Okay. Fine. Now the problem with this solution, well, not problem, but the things that need to be further fixed with this solution are the following: that that even if we have shown that this is a solution, there are two things which are not fixed. Okay, and those two things are kind of related to each other. First one is that we have not used the point mass at the origin, because we have solved r alpha beta equals 0. Okay, and r alpha beta is equal to 0 everywhere in space except at the location at which we have put the point mass which is generating this gravitational field. Okay, and in our calculation we haven't used that so far. And the other issue is that we haven't determined what C naught is. Okay, and as I said, that these two issues are actually related to each other. Okay, so in other words, if we determine C naught, okay, then it would automatically take care of point mass. Or conversely, if we take point mass into account, it will tell us what C naught is. Okay. So let's try to determine what C naught is. Okay. So to do that, let's look at the time component of the metric for sufficiently large values of the radial distance. Okay. So take rho to be very large. Okay. And ask how would the GTT component look like. Okay. Now, one point is that one should be clear about why one is trying to take rho large, and that is something which follows from the solution that we are looking at. Okay. If you look at this solution and if you take rho very large, then this quantity, okay, for the large rho has a dominant factor 1. Similarly, this expression has a dominant factor 1. Okay. So therefore, for large rho, the metric looks like minus dt squared plus d rho squared plus rho squared times the spherical metric. Okay. Which is the metric of flat Minkowski space written in polar coordinates. Okay. So it tells us that the solution that we have obtained by imposing the condition that there is a point mass at the origin, that metric is asymptotically Minkowski. Okay, far away for large rho, it looks like a Minkowski space. Okay. Now, in the large rho limit, we can see that the gravitational field is weak because these factors are going to fall off to zero. I mean, the deviation from the Minkowski space is going to be small, and therefore, in the large rho limit, we can we can kind of say that the gravitational field is weak, and we can try to ask a question that whether this problem can be related to the Newtonian gravitational potential. Okay. Now we know where the Newtonian gravitational potential is sitting around in this metric that we had written down earlier, and that is that GTT is actually -1 minus 2 phi. Okay, where this phi is the Newtonian gravitational potential. Okay. Now GTT for our solution is minus into 1 plus 1 over C naught rho, and therefore phi is actually 1 over 2 times C naught rho because of the appropriate normalization factor that we are looking at. Okay. Fine. So if you work in the non-relativistic limit, then for a point particle of mass capital M, we expect the gravitational potential to be minus gm by rho, okay, where rho is the radial coordinate. Okay, and that tells us that this factor 1 over 2 C naught must be minus g times m. Okay, there's a small change in the notation from my LaTeX file versus this. I had written G subscript N for G Newton. Here I have just written this as G, but I hope there is no confusion with that. Okay, so what we find is that the factor 1 over 2 C naught that we encounter in the gravitational potential when we solve for the metric due to the point mass, that factor 1 over 2 C naught is equal to minus g times m. Okay, fine. But the factor which actually appears in the metric is 1 over C naught and not 1 over 2 C naught. So you can write down 1 over C naught as minus 2 times gm and plug it in. Okay, and that gives you this metric. Okay, and if you recall, yesterday we got exactly the same metric by using some other technique. Okay, so this is the metric generated by a point mass source, which is located at the origin in the T rho theta phi coordinate system. Okay. Now notice one thing about this metric, that when rho is equal to 2 times gm, then the dt squared part of the metric component just vanishes. Okay. Especially at the same value, the d rho squared part of the metric diverges. Okay. this is of course related to the fact that a times b is equal to 1. Okay, so if a goes to 0, then b goes to infinity. Okay, so that's the kind of stuff. Okay, and clearly vanishing or divergent part of the metric components need little more careful study. Uh, One particular thing in this case is that it looks like the the space is singular at rho equals 2gm. Okay, but what we will see later, not right away, but what we will see later is that this is only a coordinate artifact. By that I mean that if we choose the correct coordinate system, then whatever is the location r equals 2gm in this coordinate system, translated into a new coordinate system, that r equals rho equals 2gm, nothing special happens. Okay, singularity of this type are singularities of this type are typically called the coordinate singularity. In other words, a correct choice of coordinate system would not have a singularity of this kind at all. Okay, there are various ways of looking at this fact that rho is equal to 2gm is nothing very special. Okay, we will work it out in one particular way, but that's not the only way to show that rho equals 2gm is a smooth point in this space. Okay. Now remember, like, we are looking at a point mass, and rho equals 2gm is reasonably far away from the location of the point mass. Okay. So in that sense, uh, you would have expected, given the fact that we have solved r mu n equals 0 uh, in this in everywhere in the space except at origin, you would have expected that a behavior of this kind would be a bit odd for the metric, and uh, that the metric kind of shows singular behavior when r alpha beta is actually just vanishing at that location. Okay, we'll see that there is nothing very kind of special happening due to this singularity. Okay, so this is it. This is what we would call the Schwarzschild metric. Okay, and we had seen the same metric in the last class, derived in a little different way. Okay, so any questions at this point? Okay, maybe not.
Sir,
Yes.
how does one precisely define singularity? I mean, intuitively, we see something bad happening to the metric, but
Yeah. So we'll have to define quantities which are coordinate choice independent. Okay, and if that quantity diverges, then you would say that it is singularity.
so for example, when we calculate this scalar curvature,
Yeah.
if that diverges,
Yeah.
then that is a singularity.
Then that is a singularity, because there is no coordinate change that could kind of save us from this, because scalar curvature, uh, you know, if it is diverging in one coordinate system, it will diverge in all other coordinate systems. So nothing can be done. Okay. Now you may find, like in this particular case, for example, in Schwarzschild metric case, that since r alpha beta is 0, okay, uh, r, which is a scalar curvature, Ricci scalar, would also be 0. Okay, and therefore nothing special would happen with r being r wouldn't develop any singularity. Okay, uh, so what one tries to do is to look for other scalars. Like for example, if you can construct a new scalar uh, starting from Riemann tensor, say Riemann tensor with all covariant indices, say r alpha beta gamma delta, multiplied by Riemann tensor with all contravariant indices r alpha beta gamma delta. Okay, this is a scalar quantity because alpha beta gamma delta are all contracted. Four covariant indices contracted with four contravariant indices of the other Riemann tensor. Okay, so this term is proportional to r square of the curvature, but it is a scalar quantity constructed from the curvature, and if this diverges, okay, then again the metric is singular. Okay. Now, now one doesn't have to kind of keep doing this computation, because like you may find this quantity is not singular, then can go for a term which is a higher power in curvature, and any scalar quantity that you construct, if that happens to be divergent, okay, then you would say that the corresponding geometry is divergent. Okay, and that divergence of course does not occur everywhere. It may occur uh, at a point, or on a line, or on a surface and stuff like that. It cannot be that every point in space is singular. That is like really um, if, you know very degenerate kind of solution that one is looking for. Okay, generically they are like isolated points or isolated subspaces which are likely to be divergent, where the curvature could diverge. Okay. Now the point is that like you may think that like I can construct infinite number of scalars starting from Riemann tensor, Ricci tensor, and Ricci scalar, and like how many times can I check this? Okay. And the answer is that like you don't really have to look at all those infinite fellows, because after all Riemann tensor has only 20 independent components. Okay. So you don't need to kind of check more than 20 quantities really. Okay. But the point is that like you don't even need to check 20 quantities, because even with the independent quantities of Riemann tensor, for a given metric, not that many quantities are really independent. Okay, like for example, in this case, spherical symmetry gets rid of several components of the Riemann tensor. Okay, so so much fewer components are non-trivial uh, in many of these metrics, and therefore, if you construct a finite number of such invariants, okay, they would be able to kind of pin it down whether the metric has any singularity or not. Okay, there are of course various other ways of studying the singular behavior, like things like geodesic deviation and stuff like that. Something we will kind of look at as a part of our study of this Schwarzschild solution. Okay,
Okay, sir.
Sir?
so yes,
So rho equals to 0 is in fact a singularity.
rho equals 0 would in fact be a singularity. Yeah. Okay.
Okay, sir.
So yes.
So here this time is measured in whose coordinate frame?
Sorry.
I mean this time dt.
Huh?
This is measured in whose frame?
This is measured in a frame which is at rest with respect to the point mass.
Okay.
Okay. So this is metric defined in the frame in which the point mass is at rest. Okay. So let's put it this way, that an asymptotic observer, okay, an observer who is like very far away from this point mass, okay, which sees that the point mass is not moving, would write down a metric like this. Okay. Is that fine?
Yeah.
So the observer is far away and the observer is not moving, and the observer finds that the point mass is not moving, and therefore they are mutually kind of uh, in rest frame of each other, and that fellow would find a metric which would look like this. Okay. Now there are several things that we need to kind of note about this metric. One of them is something we just noticed, that is when rho is equal to 2gm, something seems to be odd with the metric. Okay, and we have just claimed that nothing special actually happens at rho equals 2gm. We need to justify that statement. But there's something more interesting happening when rho is less than 2gm. So when rho is less than 2gm, if you look at the component of g rho rho, component of d rho squared, okay, coefficient of d rho squared, I'm sorry, okay, then you see that when rho is less than 2gm, then this quantity is larger than 1, and therefore 1 minus 2gm upon rho is actually negative. Okay. On the other hand, 1 minus 2gm upon rho as a coefficient of dt squared is negative, and but that negative sign will soak up this negative sign, and therefore this quantity actually becomes positive. Okay. So if you so from asymptotic observer's point of view, if you cross rho equals to gm, then what you would call time and what you will call radial coordinate seem to switch the role. Okay, right? So t becomes kind of a spatial coordinate, and rho becomes a time coordinate. Okay, is that clear?
Sir, that will also mean that this d omega part is expanding.
Yes, yes.
Yeah,
So
because
d omega,
there is a rho.
yeah, yeah. D omega part is, yeah. So the metric also has become effectively time dependent. Okay.
Yeah, and the light cones all rotate. I mean,
Yes. So things will start looking different. So we will do all that. Okay, as we go ahead and study this solution. But I just wanted to uh, point it out right out here that this is how it is going to happen. Okay. Now, when you draw light cones, you really don't care about the spherical part of it. But it is important to note that the light cone have switched their orientation. Okay. Fine. So before we do that study, let's do something simpler. Okay, well, relatively simpler, and that is to study a test particle in the background of this metric. Okay, so we want to kind of take this metric and roll a test particle in this space and ask what is the trajectory of this test particle. Okay, now we know what that means. Okay, what are we going to do with this? If you are trying to find out what is the trajectory of a test particle, then we are going to solve what is called the geodesic equation, right? Right. Okay. So to solve the geodesic equation, what we'll do is that we will make our life relatively simple by making a specific choice. Now remember one thing, that the problem is actually spherically symmetric. Okay. So therefore you could you could just define your spherical coordinates any which way you want. Okay. Right. I mean, it's like suppose you look at Earth. Okay, Earth is rotating about a particular axis, and therefore with respect to that axis you can define what is called an equator. Okay, but if Earth was not rotating, then you wouldn't know what you would want to call as equator. Somebody calls equator as whatever we call equator right now, but somebody may just choose some longitude and call that equator, and that is equally good. Okay, and there's nothing nobody is any more right than anybody else if Earth was completely spherical object. Okay, so it's precisely like this here. The system is completely spherical. So which quantity you want to, which direction you want to call equatorial direction is completely up to us. Okay, and therefore that freedom we can use to simplify our life and simplify the geodesic equation, and that we will do by choosing theta, which is the polar angle, to be pi by 2. Theta being pi by 2 is basically being in the equatorial plane, right? Theta equals pi by 2 is the equator. So we are looking at the trajectory of the test particle in the equatorial plane. Okay, and in addition to theta being pi by 2, we also choose d theta by d sigma, where sigma is our affine parameter. Okay, we choose that to be 0. Okay, now this choice just tells you that if you are in the equatorial plane, then if the test particle is moving in the equatorial plane, then it will continue moving in the equatorial plane. It will not change the theta value at all. Okay, now it may seem like a kind of additional constraint that we are trying to put, but that's not the case for two different reasons. One reason is that uh, the geodesic equation is a second order differential equation, and you need to give two conditions. Okay, so therefore it is kind of completely fair to choose two conditions. Okay, that is one thing. Second reason is, well, there are two more reasons actually, but they are related. So let me state them in two different ways. So same relation. Second thing is that, like, we know from the Kepler law that the motion of the planet is in the plane. Okay, planet does not rotate off the plane. Okay, so if and so if you choose that plane to be the equatorial plane for that planet, okay, then d rho by d sigma would naturally be 0. Okay, and this Kepler orbit, uh, this fact about the Kepler orbit is actually related to the fact that uh, in this particular case, it's obvious that the problem has spherical symmetry, and therefore angular momentum is conserved. If the angular momentum is conserved, then if you start off with a motion in a particular plane, it cannot go off the plane, because that would kind of change the angular momentum. Okay, so conservation of angular momentum also tells you that if you choose theta to be fixed value, then this is what would happen. Okay, fine. Now you could have said that, like, okay, I don't want to choose theta to be a fixed value, but that's nothing very great, simply because you have sufficient amount of general coordinate transformation freedom available to reorient your coordinate system back to whatever we have chosen. Okay, so uh, if you choose something not so good, it can be brought into this form by just coordinate change. Okay, so there is no loss of generality in doing this. Okay, now the advantage of doing this is that uh, that of various components of the geodesic equation, some of the components would just be trivially satisfied. Like, for example, theta equation has really nothing left in it, given that theta is held fixed. Okay, so let's look at the geodesic equation in this background. Okay, so this is what is our geodesic equation, and this is the exercise that you should have done earlier just to get the Ricci tensor components, and this is the uh, thing. I have not copied this part. Okay, so so this exercise is still for you. Okay, so uh, okay, so the exercise is the following, that we of course know what A of rho and B of rho are, but you don't have to know it right now. You choose these to be two arbitrary functions and compute the Riemann-Christoffel connections. Okay, and show that of all possible Riemann-Christoffel connections that you could write down, only non-vanishing ones are the ones which are listed here, and these are their values. Okay, fine. So there are other ones, like, gamma t theta phi or something like that. It's just 0. Okay, and you can you can check those. You write down the expression for the Riemann-Christoffel connection, and you look at the metric uh, components, non-vanishing metric components, and you kind of write down arbitrary variables on gamma, and you'll find that, like, most of them are 0 just by sheer inspection. Okay, the ones which are not 0 by inspection are the ones which you need to kind of look at little carefully, and in that also you would find roughly half of them would just vanish. Okay, by some terms cancelling and stuff like that.
Sir,
Okay, yes,
sir, since geodesic equation is simply derived from the Lagrangian, I mean,
yeah,
uh, we can simply choose a affine parameter, let's say lambda,
yeah,
and divide this equation, the metric dt square by d lambda square,
yeah,
and put a half and construct the Lagrangian, and
yes,
then use Euler-Lagrange equation to read off the non-zero. It will
yes,
become only the non-zero
absolutely,
Christopher.
absolutely. You can do that also. Yeah,
But sir, in one of your problem, I tried that, but it was on the cylinder part.
yeah.
Yeah, and there it is not working. I'm getting a non-zero. I don't know if I made a mistake, but I checked it twice.
I see.
The Lagrangian is giving something else, and explicit
And
calculation is giving something else.
I see. Let me check. I mean, I shouldn't do that, right? I mean, it's kind of obvious that it shouldn't do that. Uh,
Yeah. So
yeah,
it might be my mistake, but it is not doing.
I see. I see. Yeah, maybe
Yeah.
at some point we can sit together and try to figure out this thing. We can
Yeah.
have
Yeah. Okay.
a different session for that. It
Okay.
shouldn't happen. Maybe, yeah, maybe some minor
Yeah.
error is the
Yeah.
one who is
I did a
responsible
goof
for
up.
it. Yeah, it's possible. Yeah.
Yeah.
Interesting. Yes, of course. The world line Lagrangian is the best way of getting the non-vanishing components because it will not give you the vanishing components anyway. So that is the fastest way of doing it. Yeah. So yeah. So any which way you do it, given this, it's all up to you as to how you want to go about it. Okay. Uh, if you have any access to any symbolic manipulation packages, you can just plug the metric in and get this answer in 30 seconds. Uh, mm, and I would suggest that, I mean, since you people are away right now, you may not have access to these things, but I would actually suggest that you people should learn things like Mathematica and so on. Institute has the license, this thing, and learn how to compute this and Riemann tensor, Ricci tensor using by writing small codes on Mathematica, because going forward, that is, I mean, everybody in the world uses that kind of stuff. Nobody does calculations by hand. Okay, and this will take you even if you are very efficient, it will still take you about half an hour to get these answers. Mathematica will give you in 30 seconds. So 30 seconds versus 30 minutes. And going forward, more complicated problem will take days for you and hours for Mathematica. So it's a good idea to learn at some point.
So
Okay.
are there, I mean, dedicated packages in Mathematica for this? Because I couldn't
Yes,
find any.
yes, there are dedicated packages. There is, I forget the name.
Yeah, I mean, I couldn't find any. Tried but didn't find any package.
No, no, there is. Yeah. So, so there is one which I remember offhand. It's called TT. Uh, it's called Tools for Tensor Calculus. Okay, there is one package like that. There is one package which is written by somebody who is in Brandeis University, is a faculty there. I forget his name right now. Mm, and his package has a name. This is ridiculous. Uh,
There is, I guess, exact.
it's called,
X.
no, no, not exact. Exact is also one thing, but there is something called math-tensor.m. Okay, something called math-tensor. Okay, that is one thing that one can use, and there are various other packages also. Uh, there are various other people who have written down their own packages also. So uh, yeah, but math tensor is one thing which is very useful, in fact. Okay.
Okay.
Yeah, at least the one which I use is, I have used the TTL as well as math tensor, and both of them are quite good actually. Uh, the, the the tools for tensor, sorry, not TTL, TTC. Tools for tensor calculus is a kind of little primitive, but yeah, uh, sometimes it is good to have something primitive also. You at least know as to what it is trying to do. Math tensor is much more elaborate, can do very complicated computations also. It's a good thing. Okay. Fine. So coming back to this, of course, this part of the computation is not that difficult. sometimes once in the lifetime at least one should do this calculation by hand, so that for a different reason, in the sense that, like, you know, you do this computation by hand and then you run the same metric in Mathematica with somebody else's code or your own code. At least this is a benchmarking test on the code that it gives the correct answer, so that next time when you do the calculation, at least believe that the result is correct. Okay, so okay, so what we need to do is to use these gammas inside the geodesic equation and solve the geodesic equation for various coordinates. Okay, that's what we want to do. Okay, so let's start with the radial part of the equation. Okay, so by that I mean that we take x alpha to be rho. Okay, it can be t, rho, theta, and phi, and you just take that to be rho to start with. Then you have second derivative of rho with respect to the affine parameter plus gamma rho alpha beta with dx alpha dx beta pieces. Okay, and we need to ask what alpha beta values we can have, and that is the thing for which we need this set of gammas. And we find that alpha beta can be tt or rho rho or theta theta or phi phi, and that is it. Okay, but it still gives you four terms, so our equation will have four such pieces: tt with dt squared, rho rho with d rho squared, theta theta with theta, d theta squared, and phi phi with d phi squared. Okay, and thankfully there are no off diagonal pieces here, so it's kind of looking relatively simple. Okay, but in fact it is not as simple as it should have been, but we will make it simpler in a moment. Okay, and namely we have a condition that theta is equal to pi by 2 and d theta by d sigma is equal to 0. Okay, and that tells you that gamma rho theta theta term should just vanish because d theta by d sigma is 0. Okay, so we can get rid of this term. But there is also gamma rho phi phi, okay, which contains a term sine squared theta, and since theta is equal to pi by 2, this term is just 1. Okay, so that further simplifies our life. Okay, and therefore we can write down this expression in this fashion. So I have done it in two steps here. First, I got rid of d theta by d sigma term and wrote down this expression, and then I wrote down gamma rho phi phi in this fashion, and then we are going to substitute sine theta equals 1 here. Okay, and that reduces the phi term expression to 4 term expression, with one of the terms getting simplified because theta is equal to pi by 2. Okay, so here is the form of the equation for rho, and this is by far the most complicated expression. The other expressions are going to be simpler than this. Okay, fine. The other equation that we could write down is to take this x alpha coordinate, instead of being rho, we can take that to be phi, or we can take that to be theta. Okay, so let's start with phi. Okay, so suppose you take that to be phi, then you go back and ask what are the ones where you have phi upstairs, and you have that for two places. Okay, in these two gammas, one of the gammas contains theta here. Okay, but the theta here means that this gamma will be multiplied by d theta by d sigma. Okay, but d theta by d sigma is set to 0, so this gamma is of no use for us. Okay, and therefore only this gamma which is going to be useful, and therefore this equation contains only one term, one additional term. Okay, and that is, of course, we are going to use this gamma, okay, which is 1 by rho. Okay, but you have to notice one thing, that it is off diagonal fellow. So even if it is 1 by rho, you can write down gamma phi rho phi, which is same as gamma phi phi rho, and therefore this factor doubles up to gives you an equation which is like this. Okay, so this is the second equation. Second derivative of phi with respect to sigma plus 2 by rho times d phi by d sigma d rho by d sigma equals 0. D theta by d sigma has terms which are two of them here. Okay, again we will write down all of them right now, but again you can check that this term will vanish because the theta downstairs would have a d theta by d sigma coming with it, and that is 0. Okay, but nevertheless, let's first write down all three of them. Okay, so we have a d theta by d sigma term which is given by this factor. Again, off diagonal rho, therefore it will be 2 by rho. Okay, so you get that piece, and gamma theta phi piece, which is this. Okay, again this term is going to be 0. Okay, so we don't have to worry about that. This term is also going to be 0, because although sine theta is 1, cos theta is 0. Okay, so therefore that term also vanishes, which tells you that second derivative of theta is going to be 0. Okay, with first derivative vanishing, theta equals pi by 2 naturally solves this equation. Okay, so it tells us that the geodesic equation ensures with d theta by d sigma equals 0 that theta equals pi by 2 will be always maintained. Okay, so that is kind of satisfying, that it takes care of our initial condition being kind of not being violated by the solution of the geodesic equation. Okay, so the last thing that is left with is the T equation. And for T equation, you will see that there exists only one term, that is gamma T. We have to look for the upstairs index first. Okay, so that's a gamma T, but it's off diagonal piece T rho. Okay, so we just have to forget this factor of half and take A prime by A. Okay, so that is the only term that we would have, and therefore you get d2t by d sigma squared plus A prime by A times dt by d sigma times d rho by d sigma equals 0. Okay, good. So if you look at these equations, then you see that one equation is already solved, which kind of ensures our initial conditions are fine. The second equation that we have, which is sitting out here, has no A of rho or B of rho dependence, so we need not worry about it right away. So there exist only two equations which contain A and B dependence, which is a rho geodesic equation and T geodesic equation. Okay, so let's substitute A and B into this. Okay, so suppose you look at the phi equation first. Okay, because it does not involve A and B, you might as well kind of dispense that off. Okay, then you notice that this entire expression can be written by dividing this entire equation by d phi by d sigma. Okay, so you have a d phi by d sigma inverse times second derivative of phi is equal to 2 by rho times d rho by d sigma. And you can easily see that that expression is like a total derivative. So you can write that first term as d sigma of log of d phi by d sigma. So that when you take a derivative, you get d phi by d sigma inverse times second derivative of d phi by of phi. Okay, fine. On the other hand, when you multiply by d phi by d sigma inverse, this term goes away and you just get 2 by rho times 0 by d sigma, which is also a derivative of log of rho. Okay, to be precise, it's a derivative of log of rho square. Okay, so you get an expression from here log rho squared, and from here log of d phi by d sigma. Okay, so d sigma of this entire expression is equal to 0, which means this entire expression must be a constant. Okay, so let's put that as a constant log of some constant quantity, which is also constant. Okay, so that tells us that rho squared times d phi by d sigma is constant. Okay, good. So that kind of takes care of the azimuthal variable. The polar variable has already been fixed to be pi by 2. Okay, so we are left with only the non-trivial sector, which is the radial and time component. Okay, the time component also has the same feature, namely if you multiply by dt by d sigma inverse, then dt by d sigma goes away from here and dt by d sigma inverse comes and sits there. Dt by d sigma inverse times second derivative of d with sigma tells you that that quantity is actually a logarithmic derivative. Okay, here also a prime by a times d rho by d sigma. Remember, a is a function of rho, not of sigma, So therefore, a prime times d rho by d sigma divided by a is actually a d by d sigma of a log of a. Okay, so therefore, this entire expression can be written as a logarithmic derivative of two functions. Okay, d by d sigma of log of dt by d sigma plus d by d sigma of log of a. Okay, so clearly, you can pull this out. You write down log of dt by d sigma times a is equal to constant. Okay, this constant we can rescale. Okay, so what we will do is that we can rescale the affine parameter lambda, affine parameter sigma to soak up this factor and set it equal to 1. Okay, if you do that, then your equation actually looks like a of rho times dt by d sigma is equal to 1. Okay, so that's this equation. Excuse me. Okay, so having dealt with all three equations, the last equation is the rho equation, and that is a place which involves dt by d sigma, d phi by d sigma, which we have already determined. We'll just plug them in here and get the equation which involves rho and its derivatives. Okay, so here we go now. Fine. So so let me do one thing. Let me try to split the screen so that we can look at that equation again. Okay, so here's the equation. Okay, and yeah, maybe I will kind of stay at this point. Okay, so what we want to do is substitute dt by d sigma to be as 1 by a here. So it's going to be a prime by a squared. Okay, and d phi by d sigma to be k by rho squared. Okay, so therefore it's going to be k squared by rho to the 4. Okay, so if you do that, then you get an equation which is an expression like this. There's a 1 or 2b sitting around here, so you get a prime upon a squared times 1 or 2b. This is 1 or 2b times b prime times d rho by d sigma whole squared, stays as it is. And the last piece is coming from here, k upon rho square gives you k squared upon rho cube times b. Okay, this factor of 2 cancels with this factor of half. Okay, and gives you only a factor of 1. Okay, so this is the equation. Fine. So we'll do the same stuff again. We will multiply this equation by b times d rho by d sigma. Okay, so that we get a d rho by d sigma, b times d rho by d sigma sitting around here. B goes away from various equations. This term will become d rho by d sigma cube. Okay, but nevertheless, we will keep that as it is. Okay, but d rho by d sigma times second derivative of rho can be converted into a first derivative equation in this particular form, d by d sigma of d rho by d sigma whole squared. Okay, that is the first term which is multiplied by b. Okay, this expression would have a prime times d rho by d sigma divided by a squared. You can check that that can be written as minus d by d sigma of 1 over a. Okay, and the third term is the one which you just have to keep as it is. 2 times b gets cancelled. You have a b prime times this quantity cube. Okay, and the last term is written out here. Okay, one can of course write this also as the total derivative. Actually, it's just d by d sigma of 1 over rho squared, which would be the quantity that we want to write down. Okay, so what you can do is kind of rewrite this entire expression as a total derivative. Okay, remember there's a b times d by d sigma acting on this fellow, and there's a b prime times d rho by d sigma cube. Okay, so what you could do is that you can check that this term and this term can be pulled together as a total derivative. Why? Because b prime sigma can be written with one of the d rho by d sigma can be written as d by d sigma of b of rho. Okay, and therefore first term and the third term sits together as d by d sigma of b times d rho by d sigma whole squared. The second term is just minus 1 by rho d by d sigma is pulled out, and the last row, as I told you, is just k squared upon rho squared. Okay. So now we see that the term in the parenthesis must be a constant, simply because it has no affine parameter dependence. Okay. So we'll set that equals some other constant n. Okay. Fine. Now, affine parameter is just something which has been used for parameterizing the trajectory, but what we really want to do is to find out how the trajectory, how the radial value of the trajectory depends on time. Okay, so what we'll do is we'll eliminate sigma by using the T equation. Okay, so T equation is kind of easy. Where is it? Okay, so is the T equation. dt by d sigma is just 1 by a. So if you multiply by d sigma by dt or dt by d sigma inverse, okay, that is like multiplying by a inverse everywhere. Okay, so that's what we'll do. Okay. So here's the first step that we do. That we look at this equation, d phi by d sigma, we multiplied by that by d sigma by dt on both sides. But d sigma by dt can also be written as a of rho. So that's how you get this equation. So rho squared times d phi by dt is equal to k times a of rho. Okay, so this is one equation. The second equation that we can simplify is the equation written up here. Okay, that would require multiplying by d sigma by dt whole square here. Okay, and that is equivalent to multiplying by a squared everywhere. Okay, so you get b times d rho by dt whole squared. Multiplying by a squared takes the a to the numerator. Multiplying by a squared gives you a squared sitting around there. Okay, so you get this equation by using the fact that dt by d sigma is 1 over a. Okay. So is that okay? Are you with me on this?
Yes, it's okay.
Okay. Okay, then let's go ahead. And so let's consider the line element that we are looking at. Okay, so let me just kind of close it down right now. So this was our line element, and we want to ask a question as to what is this object. Okay, that's what we want to understand. Okay, or what is this object? Doesn't matter which way you want to look at it. So if you are on a surface where theta is equal to constant, okay, then you can look at d tau by d sigma term. So d tau by d sigma squared to be precise. Okay, that would kind of convert this element into a times dt by d sigma squared plus b times d rho by d sigma squared plus d rho plus rho squared times d phi by d sigma squared. D theta term wouldn't exist simply because theta is fixed. Okay, so this is what you get. Okay, sine squared theta term also doesn't exist simply because it is equal to 1. Okay, fine. So now let's substitute what dt by d sigma is, which is 1 over a squared. So it gives you minus 1 by a. This quantity is something we know, which is the quantity written up here. Okay. So d rho by this b times d rho by d sigma whole squared is written in terms of these quantities. Okay, so we'll see what we get. Okay, and d phi by d sigma is k by a, sorry, k by rho squared. Okay, so we just substitute that. So you substitute that quantity as k squared by rho to the 4, cancel rho square, you get this expression. Okay. Now you compare this with what we had earlier. Okay. So here's the expression that you have a b rho times d rho by d sigma whole squared minus 1 by a term plus k squared by n squared. Okay, and that tells you that this entire term should be just equal to n. Okay, so d tau by d sigma whole squared is just a constant. Okay, fine. So this is what this rho component of the geodesic equation tells us, that affine parameter versus the proper time relation is defined up to a constant. Okay. Now, what is that constant would determine what's the particle that we are looking at. For example, if you take n is equal to 0, then that would tell us that we are actually looking at massless particle, because d tau squared would be 0. That okay. If you want to look at massive particle, then of course you would have to take n less than 0. Okay, and that would give you a massive particle equation. Okay. Fine. Okay. So now what we have done so far was to use dt by d sigma equation to get rid of sigma. Okay. But what we could do now is we have two equations, remember, here. Okay. And what we could do now is we can use d phi by dt equation to get rid of t and write down rho as a function of the azimuthal angle phi. Okay. Now, why we want to do this and not something else depends upon what is it that we want to use it for. Okay. So our purpose of trying to eliminate t in lieu of the azimuthal variable is because we want to ask what is the trajectory of a particle with some impact parameters impinged on the massive point particle with mass capital M. We want, with some impact parameters, say b. Okay, we want to ask what is the trajectory of that particle, and we want to ask the equation for the trajectory as a function of azimuthal angle, how the radial variable changes as a function of azimuthal angle and not as a function of time. Okay, and that is the reason why we want to eliminate t in lieu of phi. Okay, fine. So what we will do is, where am I? Yeah, so here. Okay, so what we will do is that we will look at this equation. Okay, so let me kind of roll it down here. So we want to use this equation, and we want to write d rho by d phi. Okay, and that can be done by multiplying by d phi by dt to the minus 2 everywhere. Okay, so if you multiply by d phi by dt to the minus 2 power everywhere, then at some places you use d phi by dt to the minus 2, at other places you just divide by ka upon rho square whole squared. Okay, so that's what we will do. Okay, fine. So what we get is the expression like this: b of rho times d rho by d phi whole squared times ka squared upon rho to the 4. Okay, which is equivalent to doing nothing, just multiplying by 1, minus a plus k squared by rho squared minus n times a squared equals 0. Okay, so this expression is just pull this fellow on the other side, write 1 is equal to all the quantities and readjust. Is that okay? Is that fine?
Yes, sir.
Okay, good. So what we'll do is we can kind of readjust this expression by dividing by a squared. Okay. So there is a squared here and a squared here and a here. So if you pull out a squared, you get 1 over a here again. Okay. And you can simplify this. I mean, trivial simplification. There is really nothing out here. Okay. This is a quadratic equation for d rho by d phi. Okay. And we can just simplify this by pulling the terms on the right hand side and taking a square root. Okay. Fine. So just check it carefully. You get n minus k squared by rho squared plus 1 by a divided by b whole to the half times rho squared by k. Okay. That is because you get d rho by d phi squared. So you are just taking square root. Okay. I have chosen positive sign of the square root. Negative sign wouldn't give you anything different really. It's just a question of how it's bending. Okay. Good. So what we'll do is we'll just invert this because right hand side is purely a function of rho. Okay. So what we'll do is that we'll take this entire expression and put it in the denominator and take d phi on the other side of the equation. Okay. So by doing that, we get an equation which looks like this. Okay. So right hand side does not depend on phi, left hand side does not depend on rho. Okay. So we can just compute this quantity. This will tell us as how the azimuthal angle would change as the radial angle changes. Okay, so you have a test particle coming in towards the point mass with some impact parameter, which is not visible here right now, but say some impact parameter b, and you want to ask as the radial variable changes, how the azimuthal angle changes. Okay. So what we'll do is we'll use this equation to determine bending of light due to a massive object. Okay. Now if you want to do a bending of light, then let's go back a little, or maybe on the lower one I'll scroll this thing. Remember we derived, starting from this metric, we derived d tau by d sigma whole squared to be this quantity, which was equal to n. Okay. And we said that like d tau by d sigma whole squared for a massless particle would be 0 because d tau squared proper time is just 0, and therefore that would correspond to setting n is equal to 0 if you are looking at the test particle to be a massless object. Okay. Now since we are looking at bending of light, which is of course a massless object, we will have to solve this equation by setting n is equal to 0. Okay. Is that fine? Okay, so let's do that. So I don't know whether I should do it or yeah.
Sir, you usually in mathematical operations we
Yeah.
do not multiply with some or do operations using something which can be divergent.
Yes.
Because, so when we are multiplying with a and a of rho and dividing by a of rho,
Yeah.
aren't we somehow violating that?
No. A of rho and B of rho are not divergent. No, they diverge only at a point, right?
Yeah.
It's like you write down, say, when you are studying complex variables, you have some functions which are which are called meromorphic functions. That the function is analytic almost everywhere, but it has some isolated singularities, right? You can eminently
Yes.
write down inverse of that function, no? Right? That function or its inverse is well-defined quantity. Okay. At the location of its singularity, it may not be well defined, but otherwise it is a reasonable quantity.
Or are we saying that apart from that particular point, if we are leaving that point aside, We
Yes,
then it
everything
is
is
fine.
fine. Yes,
Yeah.
exactly. So that's what we are going to do, no? That if the impact parameter is larger than 2 gm, then nothing is wrong with A or B,
Okay.
right? But we will see
Well,
later on that, like, even if the impact parameter is smaller than that, this may not be a right choice of variables, but we can use good choice of variables and nothing special happens at rho equals 2 gm. Okay. But yes, we will not be able to use these functions there, but we will use more suitable functions which would allow us to do these calculations. Okay.
okay. Also, sir, this d rho by d phi, uh, there are two roots to it. So
Yes.
the other one is radially outward particle.
Yeah. No. It's just a question of how it bends.
Oh yes, oh yes.
Yeah. So it doesn't matter really. Uh,
Okay.
so what we'll do, maybe it's already 23. So we will look at bending of light tomorrow. I mean, in the next lecture. I'm sorry. Okay.
Okay, sir.
Okay. So any questions?